All right. The next talk, we're going to continue thinking about type systems for distributed computation. In this case, we're going to be hearing from Luca about fair termination for binary sessions.
Okay, thank you very much for the introduction and hello to everyone. This is the outline of my presentation. Before coming to the main two topics of this discussion, I would like to introduce all the main ingredients that we need. So first of all, we can look at what a binary session is. A session is essentially a channel that connects a pair of processes, where each of them owns an endpoint of the session. Session types are types that are associated to the endpoints and tell how they are going to be used by the processes. Actually, when we assign types to the endpoints of the same session, we usually consider dual types. In this very first example, we can see a couple of processes, P and Q, that communicate using session X. Here on the left, for example, we can see that P is going to use X, first of all, to send a label A, then to receive a label B, and at last to send a signal to terminate the session. Q on the right is going to use X in a dual way, such that it will receive the label A, then it will send a label B, and at last it will terminate the session. Actually, when we deal with session types, we usually consider also branching points. And here you can see the two main constructs. Here on the left, we can see the choice construct, and it models a process that can choose to send the label A and continue according to T, or send the label B and continue according to S. The second construct on the right is called branch, and it models a process that can receive a label A and continue according to T, or receive a label B and continue according to S. But coming to the properties that we can prove using these very basic notions, if we consider dual endpoints of the same session and we consider only finite types, we can prove that all interactions eventually terminate. And notice that we are dealing with a liveness property. Unfortunately, this is not the case if we move to infinite types. In this case, we are only able to state that interactions will never get stuck. This is a safety property, which actually is not bad, but we would like to prove some stronger property also in the infinite case. So our aim was to develop a type system for enforcing fair termination. Fair termination means that all fair interactions eventually terminate. That is, infinite interactions are considered unfair because they violate some fairness assumption. The assumption that we made in this context is called strong fairness, and it states that every action that is infinitely often enabled is infinitely often performed. And we will see later how it works. Notice that we are dealing again with a liveness property. To conclude this brief introduction, I would like to introduce our running example that we will see many times in this talk. It consists of three processes running in parallel, which model an acquirer A that communicates with a seller B through session X, which in turn communicates with a shipper C through session Y. Here on the right, we can see the sketches of the implementations of both B and C, and we can see that B can receive on session X an add label if the acquirer adds an item to the cart and then it continues according to itself, or it can receive a pay message if the acquirer pays the items. Here we can think that B is going to close the session X, and then it contacts the shipper on session Y. Now we can focus on the type of X in the seller, which can be modeled by the following session type T. It is a branch between an add message and a pay message. If it receives add, then it continues according to T. So we expect that the client is going to use X in a dual way. So according to this T bottom, which is the dual of T. It is a choice between the add branch and the pay branch. Here on the right, we can see the sketch of the implementation of A. Actually, it may happen that X is used by A in a different way. For example, A may add, may add an odd number of items to the cart, and this process, roughly speaking, behaves well with the seller that you saw at the top of the page. So we need a relation that models the discrepancy between the actual and the expected behavior of a process. And so we relied on a subtyping relation. Okay, coming to subtyping, first of all, we can have a look at the original subtyping relation proposed by Gay and Hall. Again, we consider the type of X in the seller and its dual, and as we saw, these two types behave well. But T behaves well also with respect to the client R that adds at least an item to the cart. Or at the same time, it behaves well with the client S that adds an odd number of items to the cart. And this subtyping relation clearly induces a substitution principle that here I'm going to show from the process's point of view. The idea is that if T is a subtype of S, then a process that uses the endpoint according to T can be substituted with a process that uses the endpoint according to S. Unfortunately, we found out that this original subtyping relation is unfair in the sense that it is studied to preserve safety but not liveness. To see why, we can recall the strong fairness assumption that I mentioned at the beginning, which states that every action that is infinitely often enabled is infinitely often performed. Here we consider the original acquirer and seller, and the assumption implies that the acquirer will eventually send pay to the seller. Unfair subtyping allows us to state that the bottom, which is the type of X in the client above, is a subtype of the compulsive shopper, which is the client that only adds items to the cart. So here we can apply the substitution principle, and we can substitute the original acquirer here with the compulsive shopper. Notice that the compulsive shopper has only an infinite execution, which is fair, but at the same time, sessions X and Y will never terminate. So to solve this problem, we relied on fair subtyping, which is a liveness preserving refinement of the original subtyping relation, which basically allows us to reject the example that we saw in the previous slide. This relation is very hard to characterize, but we managed to define it using generalized inference systems. And here we can see a simplified definition. Okay, first of all, we can focus on the three rules that are represented with this single line. These rules, interpreted coinductively, are sound and complete with respect to the original subtyping relation. Hence, we have an axiom which relates termination, and then we have the next couple of rules that model covariance and contravariance of input and output. Then we add this corule, which is represented with this double line, which again relates outputs, but it differs from the rule since it has only a single premise. The idea is that given a judgment, we have to find a possibly infinite proof tree in the coinductive interpretation considering only the three rules, but then we ask that each node of the proof tree must have a finite proof tree inside the inductive interpretation of the whole inference system. So for example, now we can try to relate T bottom with the type of the client that adds at least an item to the cart. And since they are related by unfair subtyping, as we saw before, we can focus directly on the inductive interpretation. The idea is that we are always able to apply this corule to consider only the pay branch, which leads to an application of the axiom. So we are always able to find a finite proof tree for the judgment. This is not the case if we try to relate T bottom with the compulsive shopper. In this case, even if we apply the corule, we will never be able to apply the axiom, and so we will never be able to provide a finite proof tree. To conclude this section, I would like to complete our running example. As you can see, I added all the constructs to close the sessions. And once again, we consider the type of X T in the seller and its dual. Now we try to type the acquirer that adds an odd number of items to the cart. And we can see that X is used by the new client according to the type S. We are able to type the acquirer by using this explicit cast construct that tells that that there is an application of fair subtyping, and so we use the substitution principle to substitute the original acquirer with the one of our interest, since T bottom is a subtype of S. Here on the right, we can see the subsumption rule which models the substitution principle. Okay, coming to the properties of our type system, first of all, we noticed that fair subtyping must be used in a very controlled way. Again, we consider the type of X in the original acquirer, that is T bottom, and if we consider unfair subtyping, we can state that T bottom is a subtype of the client that adds at least an item to the cart, which in turn is a subtype of the client that adds at least a couple of items to the cart, and so on. And the limit of this chain is the compulsive shopper. This is not the case if we move to fair subtyping. So the compulsive shopper is not the limit of the chain anymore. So the partially ordered set of session types ordered by fair subtyping is not omega complete. To see what this implies, we can recall the compulsive shopper example, but in this case, the process is defined in a slightly different way. As you can notice, we have a cast inside its definition, and we consider the types T bottom and the type of the client that adds at least an item to the cart. And the idea is that we can type the compulsive shopper using infinite applications of the subsumption rule, because T bottom is a subtype of R, as we saw before. So the idea is that if the subsumption rule is used infinitely many times, this can have the overall effect of an application of the unfair subtyping. To solve this issue, we introduced the following typing judgment, which means that the process P is well typed in gamma and has rank n, where n represents an upper bound to the number of casts performed by the process before it terminates. This clearly solves our problem because we are not able to assign a finite rank to the judgment of our interest. At last, we managed to prove the following soundness theorem. It states that if the process P is well typed, then P is fairly terminating. That is, P can always eventually reach done. And in a process of this kind, all sessions eventually terminate. Here you can see a sketch of the proof of this theorem. First of all, we proved subject reduction. And then we introduced a measure which involves the rank as well as the effort for terminating the sessions that have been already opened. And then we proved that given a well-typed process, there exists a reduct that can be typed with a strictly smaller measure. Okay, coming to this last section, first of all, I would like to relate our type system to other better known properties. So we can consider one last time the acquirer seller shipper example. And here you can see a list of related properties. The first property that we take into account is deadlock freedom. This property is too weak in our context because the compulsive shopper leads to a deadlock-free process, but at the same time, as we saw, X and Y will never terminate. Another interesting example is strong normalization. In this case, if we consider the original acquirer that can add an arbitrary number of items to the cart, this acquirer admits an infinite execution in which he only adds items to the cart. So this process is not strongly normalizing. The last property that we can consider is lock freedom. This property states that all pending actions will be eventually executed. And type systems enforcing such property assign numbers to the actions, which represent how many actions we have to wait before the one of our interest is executed. But these type systems cannot deal with those sessions that are blocked by possibly infinite actions on other sessions, which is the case of our running example. Here, as you can see, the action send y send the label ship on session y is blocked by possibly infinite actions on session x. Then, for the sake of brevity, I had to skip many details in this talk. First of all, I gave you only an idea of how inference systems, and in particular their generalization with Coriolis, work. But we use this framework not only to characterize fair subtyping, but also other interesting properties of binary session types that mix induction and coinduction. And we also managed to formalize both the framework and the proofs inside the proof assistant Agda. Then I didn't talk about higher order session types. In the original subtyping relation by Gay and Hall, we find these two rules that model covariance and contravariance of input and output. But in our work, we decided to fix invariance of both, because we found out that allowing this behavior may lead to infinitely many applications of fair subtyping, which is bad, as we saw for the compulsive shopper example. At last, we have also a type checker implemented in Haskell that is available both on GitHub and on ACM Digital Library. Okay, summarizing, we started from the fact that processes may behave differently with respect to the protocols that they implement, and so we need a relation that models the discrepancy between the actual and the expected behavior. First of all, we relied on the original subtyping relation proposed by Gay and Cole. This relation is unfair in the sense that it is studied to preserve safety but not liveness, and so we had to refer to fair subtyping, which is a liveness preserving refinement of the original relation. Then we noticed that fair subtyping must be used in a very controlled way, because as we saw, infinite applications of the subsumption rule, for example, in the typing of a recursive process, may lead to an application of unfair subtyping. So the type system must avoid too many applications of the subsumption rule. At last, we managed to prove that if the process P is well typed, then the process is fairly terminating. Coming to the conclusion, at the moment, we are extending these results in the context of multi-party session types. In particular, there exists a work by Scalas and Yoshida in which they prove liveness properties of processes starting from liveness properties of session types. But the issues that they have to face are related to the fact that they rely on a subsumption rule that does not preserve liveness. We are also working on a simpler characterization of fair subtyping. The definition that I presented in this talk have been very simplified. In particular, I simplified the Coriolis. And at last, we would like to apply these notions inside other contexts, for example, the actor model. Thank you for the attention.
All right, thank you, Luca. Do we have any local questions? Oh, back there.
Thanks so much. For programs whose termination condition is based on, say, a fixed point that has a parameter and the parameter is shrinking, are you capable of using that fact in the derivation of the type system to prove termination in your system? Or does that termination bound need to be known outside of the context of, say, a depending on a variable?
So we didn't use any math structure over the judgments, but the idea is that we have this measure which involves a pair of numbers. The first one is the number of sessions that must be opened, and the second number is the overall effort to terminate the sessions that have been already opened. So the idea is that after a reduction, this second number can increase. For example, if we choose to go in a branch which opens new sessions. But in this case, the first number decreases. So we use this method which, first of all, combines subject reduction and the proofs that given a well-typed process, there always exists a reduct that has a strictly smaller measure.
Thanks.
Are there any other questions? All right, well, let's thank Luca again.